Hello and welcome to my balcony here in the city of Berlin in Germany on this beautiful summer afternoon. And as you can see, we have an almost perfectly clear sky. According to the weather forecast, this clear sky should hold through the whole evening and into the night. And so I want to use this opportunity to take a photograph of the planet Saturn. And in this video I want to show you the equipment that I use and the techniques that we'll use to get this picture. So right now we're looking directly south, and due to the Earth's rotation about its axis here in the northern hemisphere, all celestial objects, including Saturn, will appear to move across the sky during the night from east to west. And at some point they'll cross this southern direction. We say that the object culminates on the southern meridian, and they'll do that at the time when they are highest in the sky. And so that'll be exactly in this direction. And so this is actually an ideal direction to photograph the object. And so this is the position we want Saturn to be in when we take our picture tonight. So here is a simulated view of the night sky using a program called Stellarium. And we can see that Jupiter will cross the southern meridian just about sunset, which is a little bit before 10 o'clock tonight. So we can watch out for that. And then our real target, Saturn, we can see climbing up towards the southern meridian here. And so let's speed up time a little bit so we can see when it'll be approaching our meridian. And so somewhere between 11 and midnight seems to be a good time. So let's have a look at some of Saturn's vital statistics here. So first of all, we can see that it is 120,000 kilometers in diameter, which is huge. It's 10 times the size of the Earth. After all, Saturn is a gas giant. But it is also almost 1.4 billion kilometers away from us tonight, which is a phenomenal distance. And so despite its huge size, because of this gigantic astronomical distance in fact, it only appears 18 arc seconds to our eye. That is 1/200th of 1 degree of angle. Even if we include the rings, it is still only 42 arc seconds, which is still only 1/80th of a single degree of angle. So it's tiny to our eyes. So obviously we'll need a telescope, and the telescope we'll be using tonight is this one. Now this telescope is of a type called Schmidt-Cassegrain, and the primary objective, which collects all the light, is a mirror of a diameter of 20 centimeters, which is located at the rear of the telescope, and you can see it here. And so light is reflected off that primary mirror into the secondary mirror, which is located at the front of the telescope in the middle of this glass plate. And the secondary reflects the light back through a hole in the back of the telescope into our camera. And so this telescope is made by a company called Celestron. It has an effective focal length of 2 meters, 2000 millimeters, and so that's 10 times the size of its primary mirror, which was 20 centimeters, and so we say the telescope has a focal ratio of 10. As we know, Saturn appears to move during the night, and so at 2 meters focal length it'll move very quickly. So we'll want some sort of method for the telescope to follow or track the apparent movement of Saturn. And so we'll be using this mount. And this is a type of mount called alt-azimuth. And it contains 2 electrical motors, and they will track the exact motion of Saturn across the sky so we can photograph it. So here's a view of the telescope from the other side. Now the combined package of the telescope and the mount is sold by Celestron as a single product, which they call the Celestron Nexstar 8SE. And it's a very good package for observing and photographing planets. And apart from the optical tube and the mount, there is also a tiny onboard computer with a hand controller. And we'll use that to set up the telescope's alignment and set it tracking Saturn so that Saturn remains relatively fixed on the camera sensor while we photograph it. The light coming from Saturn will first travel across the mirrors in the telescope, and ultimately it'll land in the camera, which is that red thing you can see on the right here. Now to improve the image quality as best as possible, I'll use a few extra optical components between the telescope and the camera. Together they make up what we call the imaging train. At the end of the imaging train is the camera. This is a dedicated astronomy camera made by the Chinese company ZWO. It's an ASI 224MC, which is an excellent color planetary camera. and I can connect it to a computer using this USB cable. Now this camera records both infrared and visible light. So to keep the colors as natural as possible, I'll want to block the infrared light using this infrared cut filter. And to a human eye, of course, it looks transparent because it allows visible light to pass. But it will make sure that no other wavelengths of light reach the camera sensor. Now I can screw it onto the front of the camera like this. There we go. And now that's ready. Next in the imaging train is this gadget, called an atmospheric dispersion corrector, also made by ZWO. Dispersion is the technical term used to describe the prism effect. When light is refracted or bent, for example by glass, different colors are in fact refracted more or less, depending on their wavelengths. And in a prism, this causes us to see a rainbow. Now it turns out that Earth's atmosphere acts like a giant prism for light coming from distant objects like Saturn. Because our brains don't account for refraction, they simply assume that light comes in along straight lines. And so Saturn appears higher to us than it really is. Worse than that, the blue light from Saturn is actually bent more than the red light due to dispersion. And so we see Saturn as bluish towards the top and reddish towards the bottom. You can see that quite clearly here, and it'll make the image difficult to focus. So if we could somehow refract the light from Saturn back again in the opposite direction, then we might hope to undo the dispersion caused by the atmosphere. Well, that's exactly what the atmospheric dispersion corrector, or ADC, does. It actually contains two prisms, which can rotate with respect to each other. By rotating their relative positions, we can vary the amount of refraction they cause. When the two levers are parallel like this, the two prisms cancel each other out, and the ADC essentially does nothing. However, as I move the levers further apart, you'll notice that the light appears to come from lower down, because the prisms are actually refracting light upwards. Once again, due to dispersion, blue light will be refracted upwards more than red light. And so if we set the refraction amount exactly right using the two levers on the ADC, we can hope to bring both colors exactly in focus on the camera sensor, and that should ultimately give us a sharper image. Now next up in the imaging train is the Barlow lens. And this is a 2x Barlow lens, and the effect of that will be to magnify the final image by 2 times. Now a Barlow lens is actually just a concave lens, and so it diverges light rays coming into it, which means if you just look through it, it appears to make images smaller. But if we insert that into the light path of the telescope, it will actually move the focal point further backwards by a very specific distance, which is given by this tube. And the effect of that will be to magnify the image. Now that distance is critically important. So if we screw the Barlow directly into the camera, we can see that that distance is exactly right. However, we obviously want to use our atmospheric dispersion corrector. And so if we slot the atmospheric dispersion corrector into the Barlow lens and then insert the camera into the rear end of the atmospheric dispersion corrector, you'll see that that distance is totally wrong. We are much longer than the required distance for that Barlow lens to work properly. And so the magnification won't work. So fortunately, this Barlow lens can actually be taken apart. So I can screw off this front bit, which is the actual concave lens, from the hollow tube, which guarantees the correct distance. So this is the concave lens, and this is simply a hollow tube. There's no optical elements in there. So we can dispense with the hollow tube and recreate that correct distance using the atmospheric dispersion corrector. So I can screw the front off of that atmospheric dispersion corrector. That too is simply a hollow tube. And now I can use this little ring, which is actually a filter adapter which adapts the T-ring threads from the atmospheric dispersion corrector to the 1 1/4 inch threads used by many filters, and conveniently also by my Barlow lens. And so it's a little bit fiddly to get the threads to line up correctly, but you can get the hang of it. And of course you really only need to do this once you've got your imaging train set up. You can keep it. There we go. So now that's threading nicely into the ADC, or I can. There are some holes in this ring, and so I can screw it in firmly that way. And I want to move it as close as I can to the prisms inside the ADC. There we go. Now that's snug. And now I can screw the concave lens from the Barlow into that filter adapter. And there we go. So now we can check the distance, compare it with the hollow tube from the Barlow lens, and we see that we're missing a bit more than 1 centimeter to make it work properly. So what we'll do is we'll extend this distance by screwing off the adapter from the rear end of the ADC and inserting a 1 centimeter spacer. So that's simply a T-threaded ring, which is exactly 1 centimeter in length. And then we'll reattach that rear end the right way, obviously, from the ADC into that spacer. Okay, so now let's slot in the camera and see how well we did. Okay, and now let's compare that to the exact distance that we need, and we can see that we're just a few millimeters short. So I can simply move that camera back a little bit, and that should be exactly right. So now I can tighten these screws to fix the position, and that is our imaging train fully assembled. Now we can attach this piece, which is simply an adapter for the telescope. So that's a T adapter which goes into the ADC, which also contains the Barlow, and that can be screwed directly onto the rear of the telescope. And there we have it. That is our complete imaging train that we'll be using to capture the light from Saturn going through the telescope into the camera. And so on the telescope we can now unscrew the visual back and the star diagonal, which came with the telescope and which you would use for visual observation with eyepieces. So we don't need any of that, so we can just unscrew it. And in its place we can screw on our imaging train, which we just assembled. And so that fits on nicely using that Celestron T adapter. And there we are. And finally we can attach the USB cable from the camera to the computer. And there we are, all done. So to record footage from our camera, we'll be using a freeware program called FireCapture. And FireCapture is specially designed for capturing footage from astronomical cameras, particularly planets. So as we open up the program here, you'll see it connected to our camera, ASI 224MC, and you'll also see that at the moment the image is totally overexposed, and that's because I obviously use this camera mostly during the night, and so for these daytime conditions the gain and exposure are much too high. So we can bring the gain down. Gain is essentially the same as the ISO setting on a DSLR, and we can reduce the exposure time a bit. And I'm looking at the histogram at the same time to make sure that none of our color channels are maxing out. But as I'm doing that, you'll notice that I'm still not getting a sharp image, and that is because the telescope isn't focused, so we need to focus that. Now on my telescope, I've replaced the standard manual focus knob that came with it with this electric focus motor, and that gives me a lot more precision when focusing the main mirror of the telescope. And I can control that motor from the hand controller. So from the menu, I can choose the focuser option, and then I can choose to move in or out, and I get a choice of 3 different speeds, and I can now use these arrow keys to move the primary mirror to try and achieve focus, and I get a numerical readout of where my primary mirror is. So while looking at the image from the camera on the computer screen, I can now use those arrow buttons to move the primary mirror with the focus motor to try and achieve focus. And so we're getting closer, and there we are, we're in focus. So as you can see, I've pointed the telescope at some roof tiles on a house which is about 80 meters from my balcony. Notice how the image jiggles around a lot and moves in and out of focus. Those effects are entirely due to the turbulence in the atmosphere. We usually don't see that turbulence with our naked eyes, but at these high magnification levels that we're getting through the telescope, we can see just how turbulent our atmosphere really is. And of course the light coming from Saturn travels through all of the atmosphere, not just 80 meters like these roof tiles. And so we can get a sense of the challenge we face when trying to photograph celestial objects from the ground. Okay, so let's talk about some of the features in the FireCapture program, which, as I mentioned, is specialized for astronomical imaging, in particular planets. At the moment, we're seeing the entire field of view that the camera sensor can capture through the telescope. But as we saw at the beginning of the video, Saturn will appear very small to us here on Earth, and so will only take up a small area in the center of the field of view. So if we were to start recording like this, we'd be capturing Saturn, but we'd also capture a huge area of black space around it, which is a total waste. So what we want to do is to use this region of interest feature in FireCapture so that we only capture the central part of the camera sensor. And from experience, I know that this is about the correct size for Saturn. And we can use this zoom function, so it's a bit easier for us to see on the screen. FireCapture allows us to group settings together into profiles, and so right now we're using a profile for Saturn. The profile contains settings like exposure time, or the gain, or any other settings which are appropriate for Saturn. There are many different profiles. There are one for most of the planets, and there are some for some other objects, but we can add our own profiles, or we can edit the ones that are there. But today we'll just be using the Saturn profile. We can also group settings by the kind of light which we're capturing, but since we'll only be capturing visible light, we won't bother with that now. When we start capturing in FireCapture, we'll essentially be recording a video file, and so we could use the usual AVI format. However, these planet videos are quite specialized. They typically contain many thousands of frames recorded over just a minute or two. And so there is a better format which is more suited for these kinds of videos, which is called SER. So that's the video format we'll be using. At the moment, we're seeing a color image which appears to be coming from the camera. But that's only because we've told FireCapture to debayer the image. The camera doesn't actually measure the wavelength of incoming light. Instead, there's a set of minuscule color filters over each pixel in the camera called the Bayer matrix. And so the camera actually only sees a black and white image. And so if I turn debayering off, I can see exactly what the camera sees. I'll actually be restoring the color information during post-processing. So I'll want to record my videos of Saturn with the debayering turned off. But when I'm centering or adjusting the ADC or focusing, it would be nice to see the colors. So I'll turn debayering on during the previews, and then in the settings here, under the section for debayering, I can use this option which will automatically turn the debayering off while I'm recording and turn it back on again when I stop recording. And by using that setting, when I start recording into my SER file, I won't be recording any color data because the debayering will be off. But while I'm just previewing, it'll be on, and so I'll be able to see Saturn in color, which will help me focus. So I can start recording just to show you, and then you'll see that there's no longer any color information, and so none of it is being recorded. I'll be dealing with that in post-processing. But when I stop recording, I get my color image back. Now I don't actually want to keep that small recording of the roof tile, so I can use this feature, which just deletes the last capture. So while we're recording Saturn, we'll be recording at an exposure time of about 10 milliseconds. And at 10 milliseconds, we will achieve a frame rate of about 100 frames a second, because 100 times 10 milliseconds is 1 second. And since we're recording for 150 seconds, that should give us 15,000 frames at 100 frames a second. And we want that many frames because we want to deal with all the turbulence in the atmosphere, and so we'll be averaging them out, taking averages from these 15,000 frames in our SAR file of Saturn, so we can hopefully get a sharper image. Now, another thing that we'll want to pay close attention to while we're recording is the histogram down here. And it shows essentially what the maximum color value is for each channel that we're recording. And so if that ever goes beyond the maximum, then essentially we're losing data because we're not capturing those photons which exceed that maximum. But we also don't want to go too low, because then we'll just be getting very low numbers. So ideally we want to be in this top third of the histogram. And the way we'll do that is by adjusting the exposure time and maybe the gain to make sure that we stay in the right range. So it's now 9:45 in the evening, and so it's the middle of the evening dusk. The sun is just setting, and as predicted by Stellarium, there is Jupiter, and it has just crossed the southern meridian. And the sky is still clear, so I think we have a decent chance of catching Saturn later tonight. Alright, ladies and gentlemen, the moment of truth has arrived. That is Saturn. It is now 11 o'clock at night, and as expected, Saturn is soon to cross the southern meridian. So I'm gonna get set up so we can take our picture. So I already aligned the telescope earlier this evening on Jupiter, so all we have to do now is point it at Saturn, so that Saturn will be in its field of view, and so that it will track Saturn and keep it steady while we take our picture. Alright, so here we are back in FireCapture, and we can't see Saturn right now, but of course we're still on daytime settings, so we will turn up the gain, increase the field of view, and turn up the exposure as well, and bring the zoom back in control. We still can't see Saturn, because it's probably not exactly in the field of view, so I'm going to slew the telescope using the mount's the slewing controls, and there is Saturn. Okay, so we went far, and let's try and get it in the middle of the field of view. Now it looks really strange at the moment because we're completely out of focus, and so that hole in the middle, that's not a black hole, that's just my secondary mirror, and we'll fix that when we focus the telescope. So first we're trying to get it exactly in the middle of the field of view using the slew controls on the mount. There we are, that looks good. So now we're going to work on the focus. So I'm using the hand controller in the focus menu, and so we're going to move the primary mirror. Oh, that's the wrong way. So we need to, there we go. We need to try and get it as sharply defined as we can. A little bit more, I think. There, that's probably pretty close to focus. And now that we're in focus, we can see that Saturn is totally overexposed. So now we can bring the gain down, and I like to photograph Saturn about between 460 and 480, something like that. We can bring the exposure time down as well. And there we have our first view of Saturn. And it doesn't look great yet, and especially we can see the effect of atmospheric dispersion, so we can see a blue edge on top and a red edge near the bottom. So I want to first get as good a focus as I can get by moving out and into focus again. Now I'm noticing that the seeing looks pretty bad, so we'll have to see how it goes. Now to take care of the atmospheric dispersion, I'm going to turn the exposure and the gain way up again, and I'm going to use a special feature here in the pre-processing menu, which is the color saturation filter. And that will make this blue and this red tinge on the top and the bottom much clearer, so that we can now start working on our dispersion. So I'm going to start moving the levers on the atmospheric dispersion corrector apart, and as I'm touching the telescope, Saturn is starting to move around wildly, but it is also moving down, as you'll remember from our experience with the ADC before, and that's because of the refraction. So at the same time I'm slewing the telescope mount up, so I'm pulling the levers apart on the ADC and slowing up the telescope at the same time to try and keep Saturn in the field of view. And you'll see that the edges are slowly becoming less pronounced, but it's still noticeably bluer on the top than on the bottom, so we have a little while to go still. So yeah, it looks like that's still a bit bluer on the top, so we need just a little bit more of an adjustment. And we need to try and get Saturn, keep it in the field of view at the same time. Now I think that looks pretty uniform all around, so let's get Saturn back in the center of the field of view. Come on. Yeah, there's quite a lot of backlash on this mount, so sometimes it takes a while for a change in direction to take effect, but there we go. So alright, that's Saturn back in the field of view. And yeah, that looks pretty uniform, so we're going to go with that. Okay, so now we can turn off this filter, and we can set the gain and the exposure back to sane settings. So I usually capture Saturn about 10 milliseconds, so have a look at that. This looks a bit dark, and I'm looking at the histogram at the same time. And so remember, we want to be in that top third, so I think we can increase the exposure a little bit and increase the gain a little bit. So they'll change from one evening to another. It's center Saturn. And so now we can activate that region of interest, and as you'll see, that is just the right size for Saturn, and we can increase the zoom. So now we're going to work on the focus. So I've set the focus speed to the lowest setting possible, and I'm moving out of focus with the hand controller and then back into focus in very, very small increments, and I'm continually judging the image on the screen to see when it's the sharpest possible. And that looks reasonably close to focus. Although the seeing is really bad, so it's going to be hard to judge tonight. One feature we can use is this gamma function. So if we turn that on, usually it's at 50, but if we move it down to say 20, 25, it becomes a little bit easier to judge the focus. So let's move out of focus again with the hand controller, and once again move back in very, very small increments, judging the image the whole time. One thing I'm looking at is the Cassini division, which is the edge between the outer and the inner ring around Saturn. And on nights of better seeing, that edge would be a lot clearer and a good indication of focus. But we might get slight hints of it tonight. So it's moving out of focus again, and then back into focus very, very slowly. Starting to see the occasional frame which shows a sharper edge between the rings. But I think that's about as good as we're going to get it tonight. Okay, so we can turn that gamma feature off now, and let's slow Saturn up just very slightly so it's in the middle of the field of view. And now we can start recording. And so we'll now record 150 seconds worth of frames at 11 frames a second. Viewing in black and white because it's not debayering now. But so all that's left to do is to make sure that Saturn doesn't drift out of the field of view. So maybe we'll make slight adjustments with the hand controller. But no, now we just wait for 125 seconds more. Alright, so we're approaching the end of our recording here. We're at 6 seconds, 5 seconds left. And there we go. That's our first recording for tonight. So I captured 13,618 frames of Saturn during 150 seconds. Let's quickly check the ADC settings again, because this whole time Saturn's been climbing towards its culmination. So let's turn that filter on again, and so have a look at this edge and see if it looks uniform in color. And actually it does. So yeah, I don't think we need to readjust the ADC. All right, so let's turn that off again, and let's set our exposure. I think we were at 11 milliseconds and a gain of 495. Yeah, that looks right. Another feature we can use to judge the ADC is this tool in FireCapture, and yeah, apparently we're pretty close according to that tool. So okay, I don't think we need to touch the ADC anymore. So we should have another go at focusing, because focus shifts all the time, so I like to re-evaluate the focus. And so one trick we can use is this align feature in FireCapture, and then we'll use the gamma again. And so the alignment keeps the planet in the center of the field of view as long as it's possible. So now we'll move out of focus again with the hand controller and move back into focus in very, very small increments, trying to judge the tightest focus. Yeah, maybe that's close. Let's try again. Let's move out of focus and then back into focus in very small increments. I think just a tad more. I'm starting to see the occasional frame here with the Cassini division. But it doesn't look like it's going to get any sharper than that. Okay, so let's turn the alignment off and let's recenter Saturn in the field of view using the slew controls on the hand controller. And turn the gamma off again and then start another imaging run. Here we go. Alright, so here we are a few days later, and here are all the video files which were recorded in the SER format when we were recording Saturn. Now this SER format is a very specialized astronomy format, so there aren't many programs outside of the astronomy software which can read them. But that's okay, because we intend to process these files with specialized software anyway. So the first program we're going to use is called AutoStackert, and so we'll be using AutoStackert version 3, which is freeware, just like FireCapture. And so we'll just go ahead and open one of the files. So I'm already in the right folder. And so let's just start with the first video which we recorded, which is this SER file. Alright, so we get two windows. This is kind of a control window, and this is a window where we can see what's happening. So first of all, AutoStackert has actually detected that this data was taken with a camera which has a Bayer matrix, and it's even detected the correct kind of Bayer matrix. So unfortunately, there are all kinds of different Bayer matrix layouts, and my camera happens to use this red, green, green, blue, and AutoStackert has detected that automatically, and that usually works well, but sometimes it doesn't, and so if it doesn't, you can just change and force it to use the kind of data that you know you have here. So that's the first thing to note, is that we actually have our color data back again. Now we can zip through the image file and see what kind of frames we got. So those are these 13,000 frames which we recorded. Once again, the seeing wasn't brilliant on that night, so none of them are extremely sharp, but we'll be able to generate something from this data, and I don't think it's a total loss. So the first thing we want to do is to get AutoStackert to actually analyze these 13,000 frames. So it's going to align them, and then it's going to sort them by quality, and then we'll be able to decide how many of them we want to include in our final stack. And so first of all, we'll tell AutoStackert that we want to stack planet pictures, so we'll use this planet feature here. And then we have this quality estimator. And because we were at a gain level of 400 something, by experience I know that this value of 4 is a good value, so we'll stay with that. I don't much like this Laplace operator. Some people like to use it, but I get better results without it, so I don't use that. All the other settings are fine for the moment. They only apply for later stages anyway. So let's go ahead and analyze our set of images. So here he is, analyzing the data. And there we go. And so now AutoStackert has reordered all of these 13,000 frames and has used some kind of algorithm to estimate the quality, the sharpness of each of the frames. And so the sharpest frames will be in the beginning of the image run. Alright, and here we see a graph. So let's just not look at this green graph for the moment, but the grey graph. And this shows how the quality evolves over the video. And you see it goes up and down, but it's pretty constant, which is a good sign. And we see we have some really bad frames from time to time, and that's probably due to the bad seeing or wind or whatever. But sort of the bulk of the quality lies between, let's say, these two borders. So that's where most of the data is. Now this green curve actually shows the same quality values, but after all the frames have been sorted. And so the highest quality is at the front and the lowest quality is in the back here. And so this graph obviously slopes downwards. And it's just a representation of that same data, but ordered, just the way the frames are ordered right now. And so what I want to do, what I want to include in my stack, I generally kind of by eye estimate where the bulk of the data is. And so the bulk of the data is sort of here in this region. And what I want to do is to kind of get the good top part of that data. So I'm aiming to include, let's say, this part of the data. And by aiming it, by judging it visually that way, essentially what I'm saying is I want the minimum quality to be that bottom part of this rectangle, which I'm going for. And so that minimal quality, well, that happens to intersect our green curve here. And so essentially what I'm saying is I want the first 20% more or less of the frames. And so I can set that value here. Now it so happens last time I used AutoStackert, it was also 20%. It's a pretty typical value. And so we'll leave that for now, but I do judge what that value would be for each individual stack. And so here, according to my judgment, from what I'd like to include in the stack is kind of this block of quality, and essentially that means everything which is above this line, and so that's the first 20% in the ordered set of frames. So we'll set this to 20%. Now some other features which I like to use. Here is a normalized stack. And what that means is that if for whatever reason we get some outliers in our histogram and we record it at a particularly low level or a particularly high level, in the processing steps which will follow AutoStackert, it's very beneficial to have a reasonably standard histogram value. And so AutoStackert can actually adjust the final stack to a particular histogram value, which I've chosen 75% because that's a value which works well, and so I can use that feature here. And finally, we have this RGB align feature here. So if I hadn't used an ADC, then this option would be absolutely essential, because it essentially does in software what we've done using the ADC in our original images. Now, using the optical device, the ADC, we actually get a huge advantage over doing it in software because our original data is already reasonably aligned. But I always like to include this option in my stack to, I don't know, get out, the last possible deviations and still get every bit of extra quality out of the data. And it doesn't do any harm if the data should already happen to be perfectly aligned. Alright, so I think that covers most of the options that we'll be using here. Now, the one thing we still need to do before we can actually start stacking is we need to define align points, and those are points on the image here which AutoStackert will use to actually align the various frames with each other. So if you look through all of these frames, Saturn seems to change shape all the time, and that once again is due to atmospheric disturbance. And by setting align points, we're actually giving AutoStackert a chance to try and guess which parts of the image have been stretched in which direction from one frame to another. And so it's kind of a delicate art to choose the correct number of align points. We don't want too many and we don't want too few. And for Saturn, I usually get good results when we have somewhere between 20 and 30 align points. And I let AutoStacker place them automatically, so I think 56 is probably a good value. So if we just place some align points, then yeah, you see, that's 22 align points, so I think that's good. If we'd chosen a smaller alignment area, then if we do that, we'd have got more, so now we get 35, and that might be a little bit too much, especially with low quality data, because then, you know, some of these points, AutoStacker might not be able to deduce from the data where that point is exactly on each of the frames, and so we don't want too many of them. So I think that's too many. So we'll go back to 56. I think that's a good value. And so, having set some align points, we're actually ready. We can start stacking. So let's just tell AutoStacker to do that. Okay, so AutoStacker is done, and the image has been stacked, and essentially we're finished now with this program. So we can close it. And so you'll notice that I now have a TIFF file here, which contains the result of the stack of this video file. And so the first step now for working on that TIFF file is we'll use another freeware astronomy program, which is called Registax. Registax. Here we go. And so I can now open this TIFF file in Registax, and there it is. And so this is the result of the stack, which we just did in AutoStacker. And so we can see a little bit of detail in here, so we can kind of imagine the Cassini division here. But this is a TIFF file which contains an awful lot more information and very, very subtle levels of detail that our eye can't see. And we want to bring out that detail using the technique which we call wavelets. And so Registax is very good at working with wavelets. And so that's why we're using this program. Now the first thing we'll want to do with this image is you'll notice that it's extremely yellow. We'll see some pictures here. Let me get that out of the way. And you'll notice that Saturns, especially the rings, that they're pretty much white, maybe slightly off-white in some images, but they're definitely not as yellow as they appear in my image here. And so what's happening is that because Saturn was so close to the horizon when we photographed it, a lot of the blue light has actually been scattered, and so we kind of see a yellower Saturn than what it is in reality. It's the same reason why we see sunsets as red, or why the moon looks reddish yellow when it's close to the horizon. And so we'll want to correct that, and so Registax has a function for that, which is the RGB balance feature here. And generally the auto balance does a pretty good job, and as you can see the rings now look pretty white. And so I think that's a first improvement already. So okay, and now we get to the actual wavelets, which is where we're going to pull out these subtle differences and this subtle information in the TIFF file and actually make it visible. Now I won't go into all the details of the program. I'll just show you how I generally work with planet data. And so there are two kinds of wavelet schemes here. I like to use the dyadic one, the exponential one. And what that means is that these various levels, they will have an exponential effect on the image. So this one, you can see it here by clicking on this preview. You'll see that the data that this layer applies to is very fine level. So you can kind of see what would be brought out by this wavelet level. And this next one is quite a lot coarser, as you can tell. And so the next one after that is coarser even still. And so that's essentially the effect of this dyadic wavelet scheme. And so this fine-grained data, we can actually push that pretty far. So I tend to put that lever all the way over to 100%. And you'll notice a little bit of a change here. But the real change comes in actually applying wavelets once we've decided how much of them we want to apply. And so we can do that using these controls here. So we can set that to 110 or 120. I haven't really decided yet. Let's leave it at 120 for now. Okay. And so we can have a look at the second level, so that's this level of detail. And so we won't want to push that all the way to 100%, maybe even push that to 70%, something like that. Let's have a look. Yeah, that's about 70%. So yeah, that looks reasonable. Starting to see a bit more of the Cassini division here, and some hints of bands of clouds in the surface of Saturn. I don't know if we want to actually push. See, at some point it starts to look artificial, and I'm thinking that's already starting to look artificial. So maybe we don't want to do that. Maybe we'll just leave it like that. And then this third level, we'll want even less. So I don't know. Maybe we'll push that to 20%, somewhere around there. Oh, and yeah. I think that's starting to look artificial. So we probably don't want that much. Maybe we want 15. Yeah, even that's a bit much. Maybe we want 10. Yeah, perhaps that's all right. And I don't know, maybe you don't want to use some of these levels. So this is a very coarse level, and honestly I don't think we need it. So no matter what amount of, I don't think we need that level. So, and that's fine. There's no obligation to use all of these different levels. Usually I tend to use 3 of them, 2 or 3 of them. Now you'll notice that because we've started sharpening parts of the image, we've actually introduced a lot of noise. And that's very usual when you use wavelets. And so we can use this feature in here, the denoise feature, to actually take out some of that noise. And it works really well. So we kind of want to go the minimum amount of denoising so that we still get a relatively pleasant image. Now that looks kind of okay. There's still a bit of noise in there, but if we go too far, then we start destroying some data. I think that's okay. So we can see a little hint of a cloud band here, which is nice, and another one there. So we probably want to keep that. Now let's have a look if we can push any of these values further. I think we can get away with that just about, and then maybe. Yeah, I don't think there's much into that. So anyway, you can play around with these wavelets for forever, honestly, to try and get the perfect image. And it's a very personal kind of taste which you need to use here. And so for me, that's a reasonable result which we can get from the image data which we recorded. Now, obviously, the initial data wasn't great, and so the picture will not be fantastic either. But I still think this is a reasonable result considering our circumstances. We can certainly see that the planet is round, even oblate. We can kind of guess that there's the polar storm here. We can't see the hexagonal shape. That's really hard to see in my small telescope. We can kind of see the Cassini division here. We can definitely see the 2 types of rings, and we can even see the fact that the inner part of this A ring is actually is a bit thinner than the middle of it. So yeah, we see some level of detail here on Saturn, so that's certainly not bad. So okay, we can now save this picture which we've produced, and so now we can actually produce a usual image format, for example PNG. And so we'll save that, and there we go. That's our first processed result for Saturn. And so here we have the final result. And so this picture is based on a stack of a 150-second video of 13,000 frames, which I took from my balcony. And we can see a little bit of detail. We can see the Cassini division between the A and the B rings of Saturn. We can see some cloud bands on the planet. We can just about see the dark polar storm on the North Pole. And we can see a little bit of Saturn's shadow on the rings, just creeping behind the planets on the top left edge there. So I think, considering the circumstances, that's a pretty nice image. And so just to show you what a dramatic effect the seeing conditions can have on your image quality, here is a recording from one night earlier. And so it too is 14,000 frames. It's about the same amount of frames. But you'll notice as I scroll through the frames in this video that they are of a much better quality than the image we just processed. So you'll see that Saturn doesn't change shape nearly as much as in our video, and that's just because the atmosphere was a lot calmer, and so it was deforming the light from Saturn much less. And you'll see many frames where we can very clearly see the Cassini division. It was also easier to focus on this night, and so this is an example of reasonably good seeing, and so that's the kind of raw data which you can achieve in those circumstances. And so after processing that data, we get this image here. And as you can see, this is definitely a lot better quality. And so we can see the Cassini division very clearly. We can even estimate its size. We can see a bit of structure in the outer A ring now, as well as the inner B ring. We can even kind of see a little bit of the C ring, which is a very dark and sparse ring inside the bright white ring on Saturn. You can see it especially as it casts a little bit of a shadow onto the planet, just above the inner white ring. The cloud bands are a lot clearer in this picture, and we can even maybe sort of guess at the shape of the hexagonal polar vortex on Saturn's North Pole. But this image was produced using exactly the same technique which I showed you in this video, and so it was recorded with the same imaging train and with the same settings in FireCapture, and it was processed in exactly the same way in AutoStackert and then Registax. The only difference is that well, we simply had better seeing conditions when the data for this image was captured. So anyway, I hope you enjoyed watching me process and first capture and then process an image of Saturn from start to finish, and maybe it'll inspire you to apply some of the techniques which I have found helpful in your planetary image processing. So yeah, that's it for now. Goodbye.